Just recording. All right. So we have been talking about position, velocity, and acceleration, right? That's pretty much what we have been focused on from the beginning of the semester. We spent a good amount of time on that because it's very important for you guys to be comfortable with components of accelerations in different coordinate systems, right? We looked at how can we find position, velocity, and acceleration in Cartesian coordinate system? How can we find it in polar coordinate system, and how can we actually deal with it in normal tangent coordinate system, right? Remember, this is just one same thing. We're just using different coordinate system depending on what the problem is looking for or what the situation is that we're dealing with. Now, let's now start talking about the topic of this course, right? Dynamics. Now, if you remember when in statics, right, probably you had you were given some general idea of what engineering mechanics includes. I remember when we were talking about engineering mechanics, I told you, well, basically engineering mechanics is you can divide it into mechanics of rigid bodies, mechanics of flexible bodies, and mechanics of fluids, right? And we said mechanics of rigid bodies basically includes either statics or dynamics. The statics is for the situation that everything is in equilibrium. We introduced Newton's laws, and we said, well, the first law and the third law are the laws that we're going to be more focused on in statics. And then we said if the object is moving with a non-constant velocity, or better to say it's not in equilibrium, then that falls into dynamics, which is the topic of this course. And just for the sake of completeness, we said, well, mechanics of flexible bodies, you deal with that in solid mechanics course, machine design, when you deal with bending and torsion. And mechanics of fluids, obviously, when you have fluid mechanics, whether you're dealing with compressible fluids or incompressible fluids. So here we are, dynamics, right? Let me see if I can. There you go. Let me put everything under force. Change the board here in my office and I'm less comfortable with force, mass, acceleration. Right? So let's just forget about the general category. Let's just focus on dynamics, right? In dynamics, if we just talk about dynamics, now dynamics, you can think about dynamics, you can divide it into two categories or two different subjects. First, kinematics and then kinetics. Now, we have been talking about position, velocity, acceleration, which falls into kinematics. Now, kinematics pretty much is the branch of dynamics that describes the motion and deals with position, velocity, and acceleration. Everything that we've been talking so far falls into kinematics. All right. Just want to give you a general picture of kinematics. There you go, and then kinetics. So kinematics, position, velocity, acceleration. That's what we deal with. Position. I can try to write this board a little better. Position, velocity, and acceleration. Kinetics, right? Now this is new, right? Now we're going to start talking about dynamics, which includes both kinematics and kinetics. Now, kinetics, it deals with forces and torques, right? These are what cause the motions. These are whatever that they cause the motion. So let me just put it here. Deals with forces or torques. I have a much better handwriting with the other board. This is if you can't read it, just let me know, then I read it for you. With forces or torques that, let's put it this way, that cause the motion. So when we are dealing with kinematics, we don't care about the cause for that motion. Right? We just say, well, whatever it is, we're just looking at its velocity, just position, velocity, and acceleration. We don't care why this object is, or why this object has this velocity, why this object has this acceleration. Now, kinetics, we are focused on what is causing this velocity, acceleration, or what is causing this object to move. Now, together becomes dynamics. Right? Dynamics basically deals with objects. We study position, velocity, and acceleration, and we also study what is causing those what is causing that motion. Right? As opposed to statics, where everything was statics. Right? Nothing was moving. We were in a static equilibrium. Either you're in a static equilibrium, which basically nothing is moving, or you are just in equilibrium that the velocity is constant and it's on a straight line. So, in order to study dynamics, we have to just refresh our minds about Newton's laws. Right? We talked about Newton's laws over and over when we during statics, right, that course. Now, we introduced Newton's laws, all three of them. We were focused on first law and third law. Right? The first law was basically, we said, well, if a body is at rest or it's moving on a straight line with constant velocity, it's going to stay in that state unless there is some kind of a non-zero net force applied to it. Right? That was the first law. And second law, we didn't really deal with second law. We just introduced the second law. And we said, well, second law basically tells us what happens if this net force is not zero. What happens if there is a force or the net force applied to the object is not zero, so it doesn't fall into first law? How do we deal with that situation? That would be the second law. So it basically was telling us, well, if the force is non-zero, then you're gonna have acceleration in your so acceleration in your object. And we said the acceleration basically is proportional to force and mass. So F over m basically gives you the acceleration. And we said acceleration is a vector, is in the same direction as force, because mass is just a mass is not a vector. And the third law was basically the law for action and reaction. We said for every action there is an equal and opposite reaction. Let me just, for the sake of completeness, let me just quickly put Newton's laws, or at least some simple form of those. Newton's laws. So the first law, hopefully these are familiar to you. You've heard that, you've seen it in statics. Right? These three laws. Usually the textbooks in dynamics, they start with Newton's laws, but I talk about position, velocity, and acceleration, and then once we're done with it, I start talking about Newton's laws, because before that we actually don't use it. So it's better to just start talk about Newton's laws when we start talking about kinetics, where it comes into play when we are studying the motions of objects. Right. So first law, you can write it this way. Let's see. You can say. Let me have a good, relatively good definition. Okay. You can say, very my version, a body at rest or moving on a straight line at a constant speed continues to move in, let's make it a little easier, will remain, it's easier, probably, will remain in that state unless will remain in that state unless acted on by a non-zero net force. Oh, that's important. Non-zero net force. Basically, the way we in mathematics or terms of I would say writing it using math, we write it the other way around. We say, well, if the summation of the non-zero net force on an object is 0, that object is stay at rest if it isn't at rest, and it's going to keep moving on a straight line with a constant velocity if that's its a state at the beginning. So pretty much you just say summation of forces is equal to 0. That summed up a lot of what we covered in the statics. Right? Now the second law, expand what the first law is saying, and it says, well, what happens if this net force is not 0? What happens if summation of force is not equal to 0? How do we deal with that? How do we study the motion of an object that it's the net force applied to it is not 0? And that's where basically we talk about this Newton's second law, saying that, well, if that force or net force is non-zero, then the object is going to start accelerating. And the acceleration is proportional to force and the mass of the object. The heavier it is, and the smaller the force, the lower the acceleration. So let's put it this way. When a body is acted by, let's say, by a non-zero net force, the let me rephrase it in an easier way to go. Let's write it as the net force is equal to what should we say, to the mass of the object times its acceleration. Typically, we say it the other way around, though. But the way we deal with it, we say, well, if it's not a non-zero net force, then the acceleration is whatever that net force is divided by the mass. Right? You can just rewrite this in a probably better way. Summation of forces is equal to ma. That's the form we're familiar with. Now, this law becomes the cornerstone or the base of what we are going to work with in dynamics. We moved on from the first law. That was a statics. Things were in static equilibrium, or things were moving with a constant velocity. Now we have a body that is not in a static equilibrium or in equilibrium. That body is typically in dynamics. That body is the body that is moving, because the net force is non-zero. And as a result of that, we are going to see acceleration. And that's why we've been focused on position, velocity, and acceleration, right? We talked about position, velocity, and acceleration. Now we're going to connect kinematics to kinetics using acceleration that we're talking about, right? Basically, acceleration is the connecting link between kinematics and dynamics, if you want to think about it that way. Kinematics and kinetics. And the third law is still there. You're going to use the third law. Let's just put it in a very simple way. For every action there is a reaction. There is an actually there's an equal and opposite. There is an equal. This is the ugliest equal. There is an equal and opposite reaction. The simplest way I could put it. All right. So remember, we moved on from statics to dynamics. Right? We're still studying the we're still studying mechanics of rigid bodies. Remember, we said rigid bodies are the type of bodies that if you apply the force to them, and coming from statics, the distance between 2 points of the body does not change before and after applying the force. The example was if you have a rubber, for instance, if you pull it from both sides, obviously the distance between any 2 points on the rubber increases if you pull it from both sides. So that's not a rigid body. But the rigid body, basically, relatively, when we deal with it, I just saw your comment, Connor. I have no idea where unless. Yeah, it should be unless. Yeah, that's unless. In that state, unless, I don't know where did that come from. Yeah, unless acted on by a non-zero net force. All right. Oh, number 2. The net force is equal when a body is acted by a non-zero net force. The net force is equal to the mass of the object times its acceleration. Yeah, my handwriting gets worse on this board that I have in the office. I don't know why. Yet to figure it out. All right. So the story is we pretty much have everything we need at this point. We know how to deal with acceleration. Remember, we talked about acceleration in Cartesian coordinate system, talked about acceleration in polar coordinate system, we talked about acceleration in normal tangent coordinate system. So what are we going to add to this, to what we know in terms of acceleration, is forces. Now, again, in statics, we talked about all the possible forces you're going to deal with when you're talking about, when you're looking at an object or a particle, let's say. We haven't talked about rigid body yet. What were those forces? We had 5 forces. Can someone tell me at least few of them? What forces did we have generally, even in statics, when we introduced forces, possible forces that you have to look for when we were drawing free body diagram?
Spring forces was one. Spring force.
We had the spring force. All right.
Do tension and compression count as the same thing?
Well, let's do it this way. So 5 forces, right? Spring force. We had ropes and chains that basically are always under tension. We had weight, right? The weight always downward. We had normal force or contact, and we had friction. So 5 possible forces that every time you draw, we're going to deal with free body diagram again, that the important concept introduced in statics, right? When we draw the free body diagram, we're going to draw the free body diagram again, but there is a new type of diagram is going to be added to the whole problem solving process. So we take what we know from statics, right? Those 5 forces, you draw the free body diagram for any object that you want to study. Spring, weight, rope or chain or thread, anything that is only under tension, under tension. Weight, did I mention that? Okay, let me start from the spring, weight, rope or chain, normal force, friction. These were the 5 forces that we had to deal with. Now, same story here. You have to deal with these 5 forces, and you have to draw the free body diagram. Now, what has changed then? Well, what changed is the right side of the equation. We went from Newton's first law to Newton's second law. In the first law, we said, well, once you draw all the forces, when you find the free body diagram and isolate that and draw all the forces on your object, the resultant force should be 0. And from there, we could find all the unknowns or possible unknowns that we wanted to find. Now here, there is something on the right side, going from Newton's first law to Newton's second law, because now we have acceleration. So you still have your free body diagram that you have to find all the forces applied to your object and draw them on those 5 possible forces. And now you have something on the right side, MA, right? This part, this is new, right? This didn't exist in statics. This is from before. This you already know. Now this is new. And that's something you show on kinetic diagram, or you might see it under different names, inertial forces. And this is where what we learned from kinematics is going to come and help us. We'll look at a couple of examples. What we do is that we draw the free body diagram, show all the forces, and we make that free body diagram equal to kinetic diagram, which basically represent the right side of this equation. All right. Let's just start with something simple first. And now what we are going to do is that we are going to go over examples that we are going to follow the same kind of steps that we did for kinematics and position, velocity, acceleration. We introduced 3 coordinate system, right? Cartesian, polar, normal, tangent. Now we are going to use those 3 coordinate system again, right, and study the kinetics or dynamics of an object. Right? Over there, we were only talking about acceleration, components of acceleration in different directions, depending on what coordinate system we're dealing with. Now, we are going to use those coordinate systems and study the motion of an object, of a particle in this case. We haven't talked about rigid particle. Okay, let me just start. I'm probably saying too many things. So let's start with the first story, that was Cartesian coordinate system. Let's see how does that work for us. So Cartesian coordinates. Doesn't need to be even. Meaning that whatever we're going to study, we're going to use Cartesian coordinates to study. And you can see where does this go. After Cartesian coordinates, we look at tangent, normal, and from there we also look at polar coordinates. But how does that work? In Cartesian coordinate system, pretty straightforward. I said, well, summation of forces based on Newton's second law now, that the object is moving, it has acceleration, is equal to ma. Now, F is a vector, A is a vector. Now, if you think about, let's say, some random object, let me draw the coordinate system here in the most general form. X, let's go with X, Y, and Z. And let's say we have some, usually they show these rigid bodies or objects with some potato-shaped stuff. All right. When we are studying an object in 3-dimensional space, pretty much these vectors have 3 components, right? We can write this as this way. We can say, well, if summation of forces is supposed to be equal to ma, A being a vector in Cartesian coordinate system, F being a vector represented in Cartesian coordinate system, we can write this for each direction separately. If you want to separate that, summation of forces in X direction is equal to M, acceleration in X direction. Summation of forces in Y direction is equal to MAY, and summation of forces in Z direction is equal to MAZ. Now we can think about this accelerations, the component of acceleration along the specific axis. So these are summation of forces in X direction, summation of, I might be able to do a better job there, summation of forces in Y direction, summation of forces in Z direction. Let's see. In Y direction, now this is free body diagram. This is not new, right? You draw the free body diagram, you find the components of the force in Cartesian coordinate system. All the forces, draw them and do the algebraic sum. If they are in opposite directions, if one is in negative direction, one is in positive, you subtract them. If they both are in positive direction, either x, y, or z, we just add them up. Right? This is your free body diagram we have from before. Now, what changes is that now in dynamics, we are going to have another diagram. We are going to have another diagram that is basically, and you see it under a different name. I refer to it kinetic diagram, but you will see as different names as long as you know what it is. It represents the inertial forces, as they call it. So if you think about this as x, y, z, this is x, this is y, this is z, and we call this kinetic diagram. Because basically what it shows components of force. You multiply that by mass to be able to actually write these together. But the same object, it's supposed to be the same object, as close as I got. Now you have components of acceleration. This is new. This is we didn't have. This one we didn't have it. When this is going to be your ax, ay, az. Now we multiply that by m. M is just a constant. Ma, my, and mz. Maz. So that's how you construct these equations here. I can say, well, summation of forces in x direction is equal to max. Now, how do you know the components? M is just you multiply the acceleration components with m. How do you know ax, ay, and az? From before, right? When we were studying acceleration, position, velocity, and acceleration in Cartesian coordinates. So here is the process. You draw the free body diagram. Think about all those forces. Right. So let me break it down here for precision. What do we want to call it? Draw free body diagram with all the forces. Right, we're talking about Cartesian coordinate system, so keep it in x, y, z direction. Then you draw kinetic diagram. Representing the components of accelerations multiplied by mass. Then you make them equal. Which is summation of forces from your ma. This one, let me write it again. X is max. Summation of forces in y direction is may, and summation of forces in z direction is maz. This is coming from your free body diagram, this side, and this is coming from your kinetic diagram. This is very ugly kinetic here. So before you only had the left side, now you have the left side and the right side is added to it. You still are going to get three equations, right? One in x direction, one in y direction, one in z direction. But now the equations you have is not just forces. Now you also have components of acceleration. Right. Let's before we even draw the free body diagram, let's look at an example, very simple example of when you are given all the components in three-dimensional space. Right? Remember, the whole idea is that summation of forces is equal to m acceleration. Force is a vector, acceleration is a vector. They have components in x, y, z direction. We are talking about Cartesian coordinates now. Later on, we move into tangent normal coordinates. So we write it as tangent normal components. And when we talk about polar coordinates, we write it in polar coordinates. Let's talk about something very straightforward first before we even get into nitty-gritty of drawing free body diagram. Let's say we actually know the representation of force in Cartesian coordinate system, I, J, K components, and we can just, let's use that directly to find what we're asked to find. So in this problem says, this example says the total somehow, all right, the total external force, can say on a 10 kilogram object, it's very ugly looking handwriting right there, is constant and equal to summation of forces, you're given as 90I minus 60J plus 20K. These are components. Hopefully you remember the unit vectors. All right, just double check. Unit vectors along each axis, right? This is I, J, that is not supposed to be in that direction. I'm kind of lost there. There you go. So K, same story here. Right? These are just the unit vectors along each J. Hopefully you remember representing a vector in Cartesian coordinate. All right, so we have the total force. Right? We're given the total force. Or better to say the non-zero net force. Now what we're asked is at time t equals 0, probably second, it's the object velocity is v, the vector is equal to minus 14 I plus 26J plus 32K meter per second. So we know the velocity at a specific time at t equals to 0. Now the question is, what is the velocity at t equals 4 seconds? Now this is just a general example to show you how it could be pretty straightforward in Cartesian coordinate system. There is no object, there is no free body diagram here yet. You are directly given the force and basically just to show you how to use Newton's second law. Now I have the force, non-zero net force, right there. I know the mass is 10 kilogram. So basically I can find my acceleration vector. Once I know my acceleration vector, you can basically find my, I can find my velocity. I remember, you still need everything you learned from kinematics, position, velocity, acceleration. They're not going to go anywhere. They are, what, if anything, they're going to become more and more practical, because now once you find the acceleration based on the forces, then you can find velocity, you can find position. So whatever we learned from before, we're going to incorporate into what we are doing now, right? We're going to combine kinematics and kinetics. Kinematics, position, velocity, acceleration, we work with them. We hopefully are comfortable with it. Kinetics now is something new that we add them together to study or to basically have a picture or be able to study dynamics of an object. So in this case, acceleration is, well, let's start with Newton's second law. Right? It says summation of forces is equal to ma. So I can find acceleration, right? Summation of forces over mass. Now I have summation of forces. I have it as in terms of a vector. So 90I minus 60J plus 20K, right? Divided by mass is given 10 kilogram. This gives me acceleration as, well, you're dividing a vector by constant, so just divide every component by that constant, right? This becomes 9I minus 6J plus, plus 2K. This is the acceleration. How do I find the velocity at t equals 4? We do have the acceleration, right? So don't get lost what is going on here. We have an acceleration represented in Cartesian coordinate system, and it's a constant acceleration. 9 is the component in x direction, minus 6 is the component in y direction, and 2 is the component in z direction. This is a constant acceleration. It's not a function of time. Remember, we were talking about acceleration. We said acceleration can be a function of time, can be a function of velocity, can be constant, can be a function of display position. This is basically just a constant acceleration from what we know before. So the constant acceleration, we actually derived the equation. You can also start from, if you want, d v dt. You can start from the basic and say, well, dv is dv from v naught to whatever is the final velocity is equal to a dt, t from 0 to some t, right? And a is constant here. This is your a naught. Remember, we're talking about constant acceleration. Just wanted to see how things start fitting or coming together. So whatever you learn from acceleration, velocity, position, now you have force involved. Force is going to give you information about the acceleration or how the object moves. So you have another tool in your toolbox to study the motion of an object. Right? Now you know the cause of the motion, force. Before, you did not care about the cause of the motion. You were just focused on position, velocity, acceleration. Now, not only you deal with position, velocity, and acceleration, you also deal with what is causing the motion, forces. Or we can just, if you remember, for constant acceleration, we had v is equal to a naught t plus v naught. All right. These are all vectors, just in case. So v becomes a, which is 9i minus 6j plus 2k times t. Well, t is 4. We can't write the figure 4. Plus v naught. V naught is also given. This is our v naught right there. Velocity at t equals to 0. So this becomes, let me write it, minus 14. I can write it there. Minus 14i plus 26j plus 32k. Do the math, multiply the first vector by 4, and then the corresponding elements, you can find them by basically just adding things up. you are gonna get 22i, if I did not make a mistake, plus 2j plus 40k. This becomes your velocity. This is still, we haven't started dealing with free body diagram. But this is just very straightforward. I gave you the force in Cartesian coordinates. You could find the acceleration in Cartesian coordinates. What I'm trying to tell you here is that do not forget what you learned from before. Those are part of what we're doing here, right? Everything we learned about position, velocity, and acceleration comes handy. I could ask you, what is the position here? You have the velocity, you could calculate the position if you were given initial position, where the initial position is. Right. Question on this one, right? Before I start looking into objects dealing with free body diagram. Hopefully it makes sense. All right. Now let's look at the one that we actually have to draw both diagrams, free body diagram and kinetic diagram. Something straightforward, at least in terms of kinetic diagram. Because kinetic diagram is something that we started dealing with. We are going to start dealing with, basically. Free body diagram is something that we know from statics. Now, just to make things pretty straightforward, let's start with a block sitting on the ground. I'm going to draw it here. Let's say I have a block like this, a box maybe. And it's 15 kilograms. That's it. I even know the mass. 15 kilograms. It's sitting on the ground right there. A force F is applied to it. And we also know the friction between the floor and kinetic friction. Coefficient of kinetic friction. Now, here's the problem statement. We are told that the force F, right, force F is basically applied to this box, is applied to the box, and the coefficient of friction between the box and the surface, is point mu k, kinetic friction. It's 0.1. The box is initially, that's a very, is initially addressed, right? Now we are told that if F is equal to 20 newtons, find the acceleration for the box, and B, find the velocity for the box. Two seconds after you can say motion starts. After the motion starts. So we're going to follow now. This is the kind of problem that you, typical situation that you have to deal with. We're going to follow this procedure. That's a very ugly procedure I wrote there. Hopefully it's a little better. Draw the free body diagram with all the forces. Draw the kinetic diagram. Okay, that diagram. And then make them equal. So you can find all the unknowns you're looking for. Let's see how does this work. Let's draw the free body diagram. I'm going to draw it, what's it here? And I'm going to put the top free body diagram. So what forces do I have on this free body diagram? Out of those 5 forces.
Gravity or friction, I suppose.
I have gravity or weight, and I have friction. So let's put those. All right, let's put that here. Gravity or weight. And it's mg. I have friction. Which direction is the friction? On free body diagram, which direction I should put the friction?
To the left.
To the left, exactly. Friction is always against the direction of the motion or possible direction of the motion. So if the force is applied towards the right, to the right on this box, possible motion would be to the right. So friction should be to the left. Right? Friction is always against the motion or possible motion. So that's friction. I'm going to write it here. Fk is, let's just keep it Fk. Now what else on my free body diagram?
Force F.
What's that?
Force F that is applied.
Force F, exactly. So we have force F. What else?
Maybe the normal force.
Normal force, exactly. You are on fire today. There you go. So upward. Right? 5 forces, think about them. Weight, friction, we don't have any rope or chain here. Normal force, right? Spring. We don't have a spring here either. So every time you want to draw the free body diagram, think about those 5 forces and see which one of them you have. I can now write Fk. Hopefully you guys remember friction is mu Kn. It's kinetic friction, so mu Kn. So this is something that we know from statics. Right? Now, let's see what I'm adding to this. So I'm saying, now this is equal to, I'm going to draw another, the same box here. It's not the color I was looking for. Oh, this is new. This is kinetic diagram. Or the diagram with inertial forces on. Kinetic diagram. In this case, we are in Cartesian coordinate system. What components of acceleration this is going to have? Let's also, we have to decide about coordinate system. Let's put this as X and put this as Y. This is X. This is Y. You have to always decide about your coordinate system. With this X and Y, what component of acceleration you're going to have in this case when the force is applied to the right? Remember, we're talking about Cartesian coordinate system, so everything is in Cartesian coordinate system for me. We only have one, right? We only have acceleration to the to the right, possible acceleration. Now put it as MAX. This is new. Right? Now you have free body diagram, and then you have your kinetic diagram. Kinetic diagram representing all the components of acceleration multiplied by mass. You can think about this. Right? This is going to accelerate in this direction. It's not going to go up and down. It's on the floor. The force is horizontal. There is no Z, motion in Z direction. So the only possible acceleration is MAX. Now you have your free body diagram and your kinetic diagram. So you are going to construct, or going to use Newton's second law. You say summation of forces is equal to MA as a vector. Now, summation of forces in X is equal to MAX. Summation of forces in Y is equal to MAY. And I'll always remember to mention your positive, the positive direction, which direction you're taking is positive, so things are not confusing later on. So summation of forces in X direction, we have F towards in positive direction, so F minus Fk, which I put mu Kn. Right? These are all the forces in X component, all the forces in X direction. There's nothing else there. Now I go to the right side. That is equal to MAX. MAX. Same story for Y components. Components in the Y direction. I'm assuming upward as positive. So N minus mg from free body diagram. On my kinetic diagram, there is no component in Y direction, so it's 0. So let's see what we get. From the second one, I get N is equal to mg, right? And I can plug that back into the first one. So F, now this one becomes F minus mu K mg is equal to MAX. Remember, I'm trying to find the acceleration for the box. So acceleration, which only has one component in X direction, would be F minus mu K mg over M. And you have everything you need. Right? Your force is given 20. Mu K is 0.1. M is 15 kilogram. G is 9.81. And M again is 15 kilogram. From here, you can find your acceleration. AX. You'll get the number 0.352 meter per second squared. This is your acceleration. This is part A. Now part B, you're asked to find the velocity after 2 seconds. How do I do that? That you should know. This is from before. How do I find my velocity after 2 seconds?
Would we use the same equation we used for the last problem since it's constant acceleration?
Exactly. Thank you, Sama. So the acceleration is constant. So we already know V is equal to AT plus V naught. I'm trying to find V as acceleration, as velocity. I know the acceleration, there's only one, is AX. Time is given 2 seconds. How about V naught?
Would it just be 0? Because in the problem it says initially at rest.
Exactly. Pay attention to the problem statement. It says initially at rest. So this is 0. And this gives you, multiply that, 0.352. Closer I get to the bottom, the harder. 352 times time, which is 2 seconds. So from there, you can find the velocity after 2 seconds. I have to, oh shoot, I have it somewhere. It's 0.705 meter per second. This becomes your velocity. So again, what we are doing is that we said, well, so far we have been studying the motion, position, velocity, acceleration. We did not care what is causing that motion. Now, this is dynamics. We are bringing kinetics into the picture. We said, well, kinematics is what we were dealing with before, position, velocity, acceleration. Now we're bringing kinetics, which is basically studying the cause of the motion, meaning all the forces, possible forces applied to an object. We use this to find typically acceleration. Or let's think about it this way. Now you have a new tool in your toolbox. Not only you study the motion, but also you study the cause of the motion. Now, how do you do that? You know free body diagram from before. The new concept is kinetic diagram. Kinetic diagram is nothing but the components of acceleration multiplied by mass. You put it on your kinetic diagram and you apply Newton's second law. All right. Question on this one.
Quick question. I lost my connection on the part where you were doing the kinetic diagram. So that MAX just accounts for the whole, like the acceleration of the whole body?
Exactly. So out of, we are in Cartesian coordinate system. You're using X, Y, Z. Out of those 3 components, AX, AY, and AZ, we don't have any AY, no motion in Y direction. There is no Z here in 2-dimensional space. So the only component of acceleration is X. And we had no information about it. So I just put it as AX.
Okay. And it's the summation of all the accelerations of the forces, correct?
Exactly, in X direction. So whatever AX is, all these forces are causing some acceleration in X direction. I want to find that acceleration.
Okay, thank you.
So this one was 0. This is 0. Anyway. And remember, put your coordinate system X, Y. Pay attention to positive, negative directions. Don't get yourself confused. All right, let's do another one. Let's say we, at least let me write the problem statement. If we'll see if we get to actually solve it. Let's say I have 2 boxes now. Just make it a little more interesting. So I have one box here. And let's say this is 5 kilograms. Sitting on the ground. The coefficient of kinetic friction is 0.18. And you have a pulley here thread or a rope is passing through, and then you have another weight there. This is 10 kilogram. That's pretty much it. So we have one box. This box is attached to the other box using a rope, right, passing through a pulley. It's supposed to be a pulley. Nicest pulley I can draw. You know the coefficient of static dynamic friction between the 5 kilogram mass and the floor. The problem statement says we have two weights, right? Two weights. That's two weights are released from rest. From rest. The coefficient of kinetic friction between, let's put it this way, between the floor, between the surface and the 5 kilogram mass is k is 0.18. Right? Doesn't have a unit. So A, what is the tension in the cable after the weights are released. There you go. B, how fast the weights are moving 1 second after they are released. They are released. All right. All right. I'll go over this in next class. I just wanted to put the problem statement here. That's where we're going to start. I just want to spend some time on this one. But the idea is that now we have two boxes. They are connected. Once you have two boxes that are connected, obviously, since it's a rope, and remember the assumption we made about ropes and chains in engineering mechanics generally, in statics, and also it applies in dynamics, that ropes and chains do not stretch. Right? The length is constant, meaning that when these two are attached, from the beginning till the end, they don't have any relative motion if you want to think about it. But the idea is that they're going to have the same acceleration, right? Because they're attached to each other. I probably overcomplicated that. Just because they're attached, you can think about it as that they move together and they have the same acceleration and velocity. So that's what we are going to use to actually find what they're asked to find. We basically draw the free body diagram for the first one, make it equal to kinetic diagram, draw the free body diagram for the second one, and we'll get enough equations to solve for unknowns. But I'll talk about this in the next class. I don't want to rush it again. Okay, I just wanted to go over names, make sure that everyone is in class. We don't need to record this, I guess.